This is a short introduction to contour integrals on complex plane. Let's say you have z squared and you're trying to integrate this function over this path on the complex plane. As you can see, it's a path that connects from 1 plus I. It starts from 1 plus I and ends at 2 plus 3i, 2 and 3i. And if you subtract the two numbers, that's like the direction vector, if I use the vector calculus terms. But you don't really have to know that. You can just see that by making use of this, you can come up with the equation for the path. Because in order to calculate this, I need to use the parameterized form of this path, or else I cannot integrate. So here's the idea. You first write down the beginning of the path. It starts at 1 plus I, right? So you do that, and then plus, you put this, whatever you got, 1 plus 2i, multiply that by t. Then this will be your parameterization, because when t is 0, z of 0, when t is 0, then you end up with 1 plus I, just itself. So you're here when t is 0. When t is 1, you have 1 plus I plus 1 plus 2i, and if you calculate that, then it gives you 2 plus 3i, just because of the way we found this, okay? And any value of t between 0 to 1 will give you some values on this path. So as t goes from 0 to 1, it will draw the entire path from 0 to 1. Now, once you are convinced that the equation for this path is this parameterized equation with t being 0 to 1, now you can multiply the t out and simplify this. This is t plus 2t, and this actually becomes z of t as t plus 1 plus 2t plus 1i, just like that, okay? So that's what we got, okay? Once you have the parameterization, then we are ready to actually do the calculation. Now, the most important part of calculating the contour integral is this idea that you divide by dt and multiply by dt. So important that, let me repeat this one more time. So you have to divide by dt and multiply by dt. Now what does that achieve? Well, that achieves that first, the integration now becomes an integration in dt, so you have to know what values of t you need to use. T is from 0 to 1, so you use 0 to 1 as the endpoints. Another thing it says is that dz dt is required, so what you want to do is you want to take the z, and dz dt means the derivative, so you differentiate this. If you differentiate, derivative of t is 1, 1 is a constant, so it becomes 0. And then derivative of 2t is just 2. 1 is again constant, it becomes 0. So, and there's a I, which is a multiplication. So you know that z prime is 1 plus 2i. So that's what we need. And all I have to do is replace this dz dt by 1 plus 2i. And also, since you're integrating z squared by dt, you have to express z as a function of t. So you have to replace this z squared by this entire thing. Okay, and that gives you a very big calculation to do, which is, well, let's first think about what z squared is. Z squared is when you plug in this into z squared, so you get this, and then you just expand this by multiplication, huge multiplication, you're going to get this. And I don't want to explain this part. If you need to check my calculation, you can stop the video briefly and check if this is correct. Okay, and the result is that you end up with this integration for dt, which now you can multiply, just like how you multiply complex numbers. And the result is that you get this, you integrate that again, and you plug in 1 and 0. And when you plug in 1 and 0, you end up with negative 44 plus 7 over 3i. Okay, the calculations are pretty straightforward, so I did this really quickly. If you want to check, you can always stop the video at these moments and check if I got it right, okay? Now, I still want to show you a different way of approaching this, which is which is called the fundamental theorem of calculus for contour integrals. Well, fundamental theorem of calculus, you know that if you integrate from a to b and you have f of x dx, then it's f of x, where capital F is the antiderivative of small f, and you plug in b and a, which also can be represented as f of b minus f of a. That's what we call the fundamental theorem of calculus. Well, the same thing happens for contour integrals too, except that this condition here is not so straightforward. Often, for some functions, there is no antiderivative. So there's a technical word for such a thing. For an antiderivative to exist, you need the function to be holomorphic, or also anti-holomorphic works too. But in most other cases, you can't find the antiderivative. So if you do have a function whose antiderivative is known, then that's great. Actually, you don't have to parameterize the path and do all that that complicated calculation. You can just find the antiderivative and just plug in the endpoints, and that's it. So let me show you how that can be done for our case. See, for our case, z squared has the antiderivative 1 over 3 z cubed. Remember the power rule, right? Z to the n dz should be, you add 1 to the exponent and you put the reciprocal of that plus c. So that's the power rule, so we just use that. That's 1/3 z cubed is the antiderivative. So you just plug in these into this and calculate. And if you do, you're going to get this value, which is exactly same as the previous value that I got, which was here. I got this same value. Okay, so we get the same value that way. Now this immediately gives you some things to ponder, whether contour integrals themselves done using the parameterization of the path is really necessary or not. Well, it is necessary because in some cases it works the other way. What happens is, often if there's a way to simply calculate the contour integral and there's the parameterized version, the complicated calculation in the parameterized version can be easily calculated using this equivalence. So you still need to know how to do it by dividing by dt and multiplying by dt trick. That is very important. Now, another thing that I should tell you is that this fundamental theorem of calculus for contour integrals implies the following fact. So let's say you have some random some function f of z, and it's a function whose antiderivative is known. You can write the antiderivative. So if f of z is purely holomorphic or anti-holomorphic or some other, it satisfies some other condition so that you can find the antiderivative. If that happens, then what you can do is for any curve, you call this a closed curve if it's you can start from the beginning and come back. That's called a closed curve. So if path C is a closed path, then you can say that the fundamental theorem of calculus says, let's say this point is z1, then that's the beginning, and you go all the way around and you come back to z1, so you end up doing f of z1 minus f of z1, which gives you 0. So that means that any integral over a closed path will give you 0, provided that such a function f z exists. And that's where some surprises come in. Things that look kind of innocent actually happens to be not 0 even on a closed path. And that's actually very important. So let's jump to the next topic, which is the integral of 1 over z over the unit circle. Now the unit circle can be parameterized as cosine t comma sine t. You probably know that. I just wrote it in complex form, but cosine t comma sine t is a point on the unit circle. And if t goes from 0 to 2 pi, it wraps around the circle once counterclockwise. So for this path, let's try to do this calculation. So how do you do it? Well, again, the same trick. You divide by dt and multiply by dt, which means that you first need to find the derivative, which is this, and then you just plug in everything. So z is replaced by this, dz dt is replaced by this, and now you have this integration by dt, so the bounds are from 0 to 2 pi. And if you're wondering how to actually calculate that, you just need to multiply the conjugate of this denominator, which is this. Conjugate means you just change the plus into minus, right? So you multiply this top and bottom, and the bottom becomes, actually if you expand this, you see that this becomes 1. And once that's 1, you can expand this and further calculate. Okay? Alright, so you could proceed doing this calculation, but let me show you another way. So this is homework. If you want to really see what happens if you do it this way, after a few more calculations, you will get 2 pi I. It's not that hard. But let me show you another way to see why this gives you something none other than 0. So it's same as before. We use the same thing. It's same as before. But notice that if I take this z and multiply by I, so if I do iz, then I times cosine t is I cosine t. I times I sine t is negative 1 because I squared is negative 1. And that's exactly the same as dz dt, right? So you may realize that this is z, whereas the top one is just I times z. So what does that mean? That means that this integral is 1 over z times iz, and z cancels, and that implies that you're just simply integrating I dt over 0 to 2 pi. And if you integrate I from 0 to 2 pi, well, because this is a constant, the antiderivative is it, and you plug in 2 pi and 0, and the result is 2 pi I. Right? So that's the surprising result. Okay. Now you might wonder, doesn't 1 over z have the integral log? So why can't you use that? Well, in fact, you can use that. But even if you have the antiderivative, 1 over z is somewhat special because the antiderivative log function has a very complex structure in the complex plane. So let me explain that. So see, you were told that log can only accept positive numbers, but once you learn the logarithms in complex plane, you're told otherwise, that you can extend the meaning of the log as the log of the absolute value of z plus the argument. And argument means the angle. So see, if you have this polar form, which means that if you have some point here where the distance from the origin is r, and this angle is theta, then logarithm of that is, well, first the log of the absolute value, so absolute value of z becomes r, so you get log of r, and this angle theta is called the argument of z, so that angle is given. So that's how you extend the meaning of the logarithms to any number other than 0. Log of 0 is still undefined, but otherwise you can calculate log of any complex number. And so you can say that the, well, here's another thing I forgot to say. See, this one is another way of representing a complex number of distance r and angle theta. And this one is called the Euler form. Okay, so if you have never seen them, please take a look for the complex number in Euler form, and you'll understand why it has this strange thing. So if you write in Euler form, it's still the same thing, log of r plus theta I. Okay, so once you have the log of z, and then you try to use the fundamental theorem of calculus, in other words, you write the log 1 over z dz, and you write it as log of z, and you try to put the beginning and end points. it's slightly different. See, when you start from here, the angle is 0. But if you go all the way around this way, and you end up here, then your angle now became 2 pi. In fact, in a sense, log of z is a multi-valued function in the complex plane. So if you want to define the function on the complex plane, then you have to do something called a branch cut. So you just say that argument of z has to be giving you the value from 0 to something less than 2 pi. But you can't do such a thing, because if you go around this path, then in the perspective of this path, angle theta is always increasing. So there's some conditions in the fundamental theorem calculus for contour integrals that this has to be continuous. If you go all the way around and suddenly the angle drops down to 0, then you can't use the fundamental theorem calculus. You need to allow it to go to 2 pi. And because of that, if you plug in 1 plus 2 pi I as the final point, because the angle is 2 pi, and 1 times e to the 0 for the beginning point, because it's a unit circle, it's a distance 1, and the angle is 0. If you do it this way, then you plug in these into log, and using the formula above, when this is plugged in, it's log of r, but r value is 1, so 1 goes here. And theta is 2 pi, as I explained. You need to use 2 pi. And then this one, theta is 0, so it's log of 1 plus 0. Log of 1 is 0 anyways, but let's just say they cancel, and then this minus this simply gives you 2 pi I, exactly the same result as we did before. Now, if you look at this, again, the fundamental theorem calculus is our savior. You just need the beginning and end, and you don't have to do all that complicated path integral, and you get the same answer. Now, if you look at the solution, not only we figured out that if you integrate 1 over z over the unit circle, you get 2 pi I, but even if you had a bigger circle of radius r, then the beginning and end point will just simply be multiplied by r, which will give you, instead of 1, you just get r, and because ln of r and ln of r cancels, you just get 2 pi I. So this 1 over z is a very strange case. All the other cases, even like when you have 1 over z squared over any closed curve like that, well, the integral of this is negative 1 over z, and you don't have to be worried about anything else. You just need to say that you start from some value here, so say a, so it's from a to a, so it's negative 1 over a minus negative 1 over a, so it's 0. So no matter what you have, 1 over z to the nth power, if you integrate, because your closed path always begins at the end at the same point, you're always going to get 0. So here's what we learned so far. We found out that for any closed curve C, integration of z to the n dz will be 0, except when n is negative 1. When n is negative 1, what is that? That's z to the nth power, z to the negative 1th power is 1 over z, right? We just found out that 1 over z is something peculiar. Just because the antiderivative is log, and log is multivariable function, you end up with 2 pi I. Now, notice that I said one turn. Sometimes you might have a curve that goes like once, and then twice, and then you come back. In this case, because if you follow the logarithmic curve, it starts from angle 0 until 2 pi and then 4 pi. If it rotates twice around the origin, counterclockwise, then you're going to get 4 pi I in that case. This integral value will be 4 pi I. Also, counterclockwise is important. If you go around this curve the opposite direction, then the value will have a minus sign. All right, so all this can be put into work to find the integrals over closed curve for something that's much more complicated. So let's do an exercise just to see how powerful this is. So suppose you have an integral of e to the zth power over z cubed. This integration is hard because, first of all, there's no antiderivative for this. So it's really tough to actually do the calculation. Moreover, your path is some random path going around the origin, one's counterclockwise. So it's really hard to come up with a parametrization of this curve. So at first, this looks really challenging, but then you realize that there's something called the Taylor series or the Maclaurin series of e to the z, which is 1 plus 1 over 1 factorial z plus 1 over 2 factorial z squared plus 1 over 3 factorial z cubed. Hopefully you remember this from calculus 2. And if you replace this e to the z by this, then you can proceed to calculate this by replacing e to the z by this, and then you multiply the 1 over z cubed to each one of them. 1 times 1 over z cubed is 1 over z cubed. 1 over z cubed times z squared, for example, it will be z squared divided by z cubed is 1 over z, right? So because of that, you're going to get 1 over 2, 1 over z. And so you just do this calculation, and then you look at each of these terms. What do you find? Well, we know that all of these integrate to 0. Anything that looks like z to some power, even the constant ones, if you integrate, it gives you 0, except for this one thing. We know that 1 over z integrates to 2 pi I. So once we have this, then we can just simply say the integral is pi I, and that's it. So it makes a lot of these hard calculations really simple. And this idea later is called Cauchy residue formula, or calculus of residues. So if you look up those things, then you will find out how handy it is. And although I did this for complex integrals, you can actually use this to evaluate some very complicated real integrals too. And those are more advanced complex integrals. But once you've learned all this from this lecture, those things won't be that hard to understand. So keep working.